specialized types of ship trading nowadays, perhaps the liquefied gas carrier has the most remarkable cargo containment requirements. To see why this is so, we need first to know something about the nature of these cargoes. They are of two basic types: liquefied natural gas, LNG, and liquefied petroleum gas, LPG. Natural gas is used extensively as a fuel and also as a chemical feedstock. As its name implies, it is extracted from the ground, sometimes on its own, sometimes together with oil. LNG is a mixture consisting mostly of methane, although one field in the North Sea produces LNG composed mostly of ethane. Petroleum gas is obtained in conjunction with crude oil. Some consists of boil-off gases separated during the depressuring or stabilization of crude oil in the producing field. More is obtained from the crude oil during the fractional distillation process at the refinery. LPG, liquefied petroleum gases, are used as fuel sources and as chemical feedstocks. Most LPG cargoes consist mainly of propane or of butane. Other hydrocarbon cargoes include ethylene, propylene, butylene, and butadiene. LPG carriers may also be suitable for the shipment of such cargoes as anhydrous ammonia, large quantities of which are used in the manufacture of fertilizers. Such so-called chemical gases may require special carriage conditions. For ammonia, no brass, copper, or aluminium may be used in the system, and a few are highly toxic. Some gases require chemical inhibitors and therefore appropriate certification. For transportation by ship, the gases are liquefied, which reduces their volume by between 300 and 850 times. So the propane liquefied in this container would fill this tank as a gas at atmospheric pressure. Liquefaction. Gases may be liquefied by compressing them, by cooling them down, or by a combination of these processes. Each liquefied gas then maintains a relationship between its containment pressure and surface temperature. This relationship can be compared to the behavior of boiling water. The water molecules are constantly moving around, and some escape from the surface to form a vapor. The warmer the liquid, the greater the vigor of this process, causing an increased vapor pressure. Here, the saturation vapor pressure has equaled the containment pressure imposed by Earth's atmosphere, equal to 0 on this gauge. The surface temperature is steady, and excess heat input to the system provides latent heat to vaporize water into steam at 100 degrees centigrade. If the containment pressure varies, then the saturation temperature or boiling point will vary accordingly. Take heat away, then temperature and pressure fall accordingly. Graphs that show this relationship are called vapor pressure diagrams. Since liquefied gas cargoes are always positively contained, a similar vapor pressure curve may be drawn for each, and the temperature and pressure of the cargo will always lie at some point on the curve. At atmospheric pressure, the boiling point of a liquefied gas is below normal ambient temperatures. Butane, -1 centigrade. Ammonia, -33 centigrade. Propane, -42 degrees centigrade. Methane, -162 degrees centigrade. Some ships contain their cargoes by the use of pressure vessels. The internal pressure for some cargo then varies, depending on the ambient temperature. The tank must be able to withstand temperatures up to 45 degrees centigrade without the safety reliefs lifting. The temperature-pressure diagram shows that a pressure of about 15 atmospheres may then be expected with propane, which is reasonable from the design point of view. Clearly, we cannot build a reasonable ship to contain methane in this way, since at 45 degrees centigrade, the internal pressure would be several hundred atmospheres. If the pressure in the cargo tank is controlled, then the temperature will also be regulated. Semi-pressurized ships control the pressure to some intermediate figure. The temperature in the tanks is lowered and insulation is required. Fully refrigerated ships control the pressure to approximately equal atmospheric, thus minimizing stresses for the cargo containment system. In this domestic pressure cooker, the temperature is controlled by the setting of the pressure relief valve as demonstrated. The same principle applies to this fully refrigerated vessel. Heat ingress to the cargo through the insulation system is balanced by heat taken from the surface of the cargo as liquid is vaporized. An increase of pressure is prevented by drawing off the vapor produced, so the temperature remains constant. Reliquefaction. In LPG and ethylene ships, this vapor is turned back into cold liquid at the ship's reliquefaction plant and returned to the tank. Reliquefaction is more difficult with LNG due to the very low temperatures required, and so methane boil-off is used as fuel in the ship's propulsion unit. A problem that arises with refrigerated containment is that the low temperatures involved require the use of special containment materials. For temperatures down to minus 55 degrees centigrade, allowing the carriage of fully refrigerated LPG and most chemical gas cargoes, only slight modifications to the steel shipbuilding alloys are required. Since at atmospheric pressure, methane boils at minus 162 degrees centigrade, LNG containment systems require particularly specialized and expensive materials. Great care must be taken to avoid spillage of liquefied gases onto ordinary ship's mild steel, since this becomes brittle at low temperatures and fracture will occur. Clearly, the carriage of liquefied gas cargoes is potentially hazardous, because a major escape of cargo would lead to sudden and enormous evolution of gas, probably followed by a catastrophic fire. Major air pollution could be caused by the chemical gas cargoes, and the cold from an escape of cargo could cause further structural failure in the ship. The International Maritime Consultative Organization, IMCO, has produced a code for the construction and equipment of ships carrying liquefied gases in bulk, and each ship has a certificate of fitness to carry certain cargoes in accordance with this code. Liquefied gas ships are built to provide a greater degree of precaution against failure of the containment system than is found in normal tankers. Pressure vessel systems like this are tested before entering service by applying an internal pressure of 1.5 times the maximum pressure which should normally arise. Many gas ships apply the principle of double containment. In this fully refrigerated LPG ship, for example, failure of the primary containment tank would allow cargo to escape into the surrounding hold space. Those parts of the hull which could be cooled by contact with cargo in this way are made of suitable steel and form a secondary containment barrier. The outer hull may not be used as a secondary barrier in LNG ships since temperature stresses would be too great. This LNG ship contains the cargo in a thin membrane of invar, and a further similar membrane partway through the insulation forms a secondary barrier. The insulation and membranes are supported by the inner hull of the ship. An alternative used in this design of LNG ship is to use a relatively simple geometrical shape for the tank, without internal stiffening. The designer can then show that any cracks in the tank structure will only spread very slowly, giving time for suitable action to be taken. As well as being concerned with the achievement of reliability in the containment system, the code also requires that the cargo tanks be protectively located so that minor collisions or grounding damage should not cause release of cargo. A normal liquefied gas ship, described as belonging to IMCO Type 2G, must have its cargo containment more than 760 millimeters from the outside shell, and more than be over 15 or 2 meters, whichever is less, above the bottom. Double bottoms are fitted. A few very dangerous chemical gases require IMCO Type 1G containment. Here, even more protection against penetration in a collision is required, and so the tank must also be more than 1/5 of the overall beam from the ship's side. If a refrigerated gas carrier were to sink, any reliquefaction plant would stop, and there would be uncontrollable release of cargo through the safety relief valves. To minimize this risk, the ship must be able to withstand, without sinking, a far greater degree of collision or grounding damage than could a conventional tanker. For example, an IMCO Type 1G or Type 2G liquefied gas ship 250 meters long must be able to survive side damage 13 meters in length anywhere along her hull. Although there is great variety in the general arrangement of liquefied gas carriers, they all follow some basic design rules to minimize the risk of fire and health hazards due to cargo gas. Using the principle of the fire triangle, the ship is divided into zones where there will usually be sources of ignition, which therefore must be kept free from cargo gas, and zones where cargo gas may be unavoidable at times, known as potentially hazardous or gas dangerous zones. The safety barrier or boundary around gas-safe zones has to be carefully guarded against the ingress of gas. Accommodation ventilation, for instance, may be set to mainly recirculate during cargo operations and maintains a slight positive pressure so that any leakage will be of air passing outwards. Doors and ports are kept closed, and there are no openings in the forepart of the accommodation. The bridge front is insulated, and if fire does occur, can be further protected by a water wall, shown here by arrows pointing to the outlets. The water wall is also a protection for the lifeboat embarkation stations in the event of abandoning ship. The accommodation can be so efficiently secured in a large modern gas carrier that in the event of a mishap, such as a release of toxic vapor, it can be used as a safe refuge. The ventilation is stopped completely, and other crew members may remain inside until the ship's emergency party, wearing protective clothing and breathing apparatus, can stop the leak and check that the atmosphere has become safe again. A further gas-safe zone with positive pressure of air and airlock doors may be set up for the cargo control room and the motor room beneath, housing electric motors for compressors and reliquefaction plant. So far as possible, direct connections are avoided between the cargo tanks and the control room. For instance, pressure readings are taken indirectly through pneumatic pressure transmitters. The gas dangerous zone includes the cargo deck area, the cargo compressor room, the cargo tanks and hold spaces around the tanks. These hold spaces are potentially dangerous because of the risk of cargo vapor leakages. To minimize this risk, all connections to the cargo tanks must be made in the open above the main deck. Tank domes stick up through the main deck for this purpose, with flexible gas-tight seals around them. In modern liquefied gas ships, the hold and compressor room atmospheres are continually monitored for the presence of cargo vapors. And in refrigerated ships, Inert gas, or nitrogen, is maintained under slight positive pressure in the hold in interbarrier spaces, so that even if slight leakage does take place, flammable mixtures are prevented. Unlike many petroleum tankers, flammable mixtures are also avoided in the cargo tanks. Mixtures of cargo vapor and air are only flammable within certain limits, and when loaded, the tank contains 98% cargo liquid and 2% vapor, so the atmosphere is over-rich and consequently non-flammable. And because the tanks are always maintained at a slight positive pressure, this allows the safe use of submerged electric cargo pumps for discharging. Should the tank have to be gas-freed after discharge, perhaps for repairs, the cargo vapor remaining is displaced not by air, but by inert gas deficient in oxygen, so that the atmosphere does not become flammable. When sufficient cargo vapor has been displaced by the inert gas, fresh air can then be introduced to make it safe for entry without at any time passing into the flammable region. Before reloading the tank, the first step is to replace most of the air with inert gas, before allowing cargo vapor into the tanks. Because of the contractions involving the cool-down, commencement of loading on refrigerated vessels must be carried out slowly and carefully, as laid down in the vessel's operating manuals. The complexity inherent in liquefied gas carriers and the nature of the cargoes mean that there are a number of potential dangers to personnel which must be guarded against. Where highly toxic cargoes are worked, it may be necessary to wear breathing apparatus, especially in enclosed spaces such as compressor rooms. Additional respiratory protection, such as escape breathing apparatus, is available for everybody on board, so that the ship can be safely evacuated if necessary. Suitable test equipment, fixed and portable, is available for testing for cargo vapor in open or enclosed spaces. Due to the widespread use of inerted atmospheres, it is important that tests for 21% oxygen be considered before allowing entry to enclosed spaces. The combustible gas indicator and toxic tester are also required. Escape of liquid at leaking joints and glands could be dangerous both to personnel and to the ship's structure. Personnel will need protective clothing to guard against cold. The ship is protected by running water over the affected areas, again shown here by arrows pointing to the outlets. LNG ships are so vulnerable to this type of damage that deck areas near the manifolds may be sheathed with wood, and during cargo work, water is left running continuously over manifolds and tank domes. Should cargo fire occur, the requirement is to stop the escape of cargo and so starve the fire. If the fire is extinguished in other ways, there is a risk that a larger cloud of flammable gas might reignite. Releasing the air pressure from the emergency loop line causes pumps and compressors to stop and main valves in the system to close. Fixed and portable dry powder extinguishing equipment is supplied to knock down the flames if necessary. Remember to follow the correct procedures. The water spray should be used for cooling purposes to prevent reignition. Always thoroughly check the equipment and ensure it's in a safe working condition. Information concerning many aspects of safe operational practice may be found in the ICS Tanker Safety Guide, Liquified Gas, including data sheets describing many gases carried. Also in the booklet Safety in Liquified Gas Tankers, published by the International Chamber of Shipping, in which basic principles and definitions are available. The IMCO code for the construction and equipment of ships carrying liquefied gases in bulk should also be consulted. You must ensure that you are familiar with your own company's safety rules and regulations. Pay full attention to the sections Plant and Equipment and Ship and Shore Personnel, including those involved with the operation of your particular vessel, and to be alert at all times to meet any emergency. Although the potential hazard from liquefied gas cargoes is great, the stringent additional precautions taken for the design, equipment and operation of these ships have resulted in a commendable safety record. For safe operations, follow these basic principles. Always understand the operation in hand. Know your commitment within the vessel and your team. Never take chances or assume anything. Always check and double check. And remember, you have a responsibility to yourself, your shipmates, owners and ports of call. So know your vessel, follow procedures, and give 100% attention to your duties at all times. So if you think you've checked, check again.